The topic of geometric sequence and arithmetic sequence is an opportune moment for you to work on your skills in using spreadsheet. Spreadsheet softwares like Excel. And that is what we shall do here. We shall show you how you can use Excel to produce the elements of a geometric sequence and also produce the sequence of partial sums. So we are still on the topic of finding the sum of a geometric sequence. Let's say, for example, this is our sequence. 5 times 1/3 raised to n minus 1. So is this convergent or divergent? Well, what I mean to say is, if we were to get the sums, the sequence of sums of this geometric sequence, is it going to be convergent or divergent? Will it give us a finite sum or not? Well, all we have to do is pay attention to the common ratio. If the absolute value of the common ratio is less than 1, then our geometric sequence has a finite sum. And the sequence of partial sums that arise from computing the sum of this geometric sequence is convergent. We have a theorem that will tell us what is that sum. Well, this is the sum. It's a sub 1 over 1 minus r. So our first term is 5, and our common ratio is 1/3. So 1 minus 1/3 is 2/3, and 5 over 2/3 is the same as 5 times. Okay, so this is basic math. Many students still don't get this. 5 divided by 2/3 is the same as 5 times 3/2, and that is equal to 7.5. So this is the sum of the terms in your geometric sequence, which is defined by this. Again, this is an opportune moment for you to practice your skills in using spreadsheet. Spreadsheet is a convenient software to study sequence, because in order to produce the terms of your sequence, all you have to do is to enter your formula. Okay, you can enter your formula here, and then you will copy the formula and paste. And so it will produce this list of terms for the first 10 terms of this sequence. What's so nice about worksheet, or in particular Excel, is there is an option there wherein you can produce the scatter plot of your sequence. So a sequence is a function. A sequence is a set of ordered pairs. Look at this. 1, 5, 2, 1.667. Each of these is an ordered pair. So you can look at it as the coordinates of points in your XY plane, and you can graph it. What's so nice about Excel is it just takes 2 clicks to produce the scatter plot. You highlight this, you click insert, and you click that function. It will produce this scatter plot. Okay, so how do you interpret this scatter plot? Well, the first term is 5. That is 5. The second term is 1.667. How did you get here? You multiply 5 by 1/3. And so that is that point. Then you multiply 1/3 to 1.667. It will give you 0.556. And that corresponds to that point, so on and so forth. And so this is an example of a descending sequence, because your common factor is a positive real number less than 1. So it is always reducing. It is reducing the size of the preceding term. That's why it becomes a descending sequence. We shall now produce the sequence of partial sums. Again, our interest in this part of our discussion is to find the sum of the geometric sequence. And we can do that by adding the terms one by one. So how do you produce this? Okay, so this is the first sum. So you add the terms one by one. So you add 1.667. This is the second term to the first term. It will give you 6.67. You will add the third term to the previous sum. So 0.556 plus 6.667, it's 7.22. Now again, it's so nice to use Excel for this is because all you have to do is upon writing the formula here, you just copy and paste it, and it will give you those terms. So these terms at the bottom are the first 10 terms of the sequence of your partial sums. Your worksheets have an option to produce the scatter plot. And this is the scatter plot for the terms of the geometric sequence and for your sequence of partial sums. Okay, so our sequence of partial sums would be the orange dots. So the first sum is 5. The second sum, S2, is 6.667. The third sum is 7.222. The third sum, so on and so forth. Well, if you were to look at it, the sequence of partial sums is organizing itself around a particular real number, and that real number is 7.5. And in fact, that is the sum that we got for this particular geometric sequence. Let us go to another geometric sequence. How about this? Is this convergent or divergent? Does this geometric sequence have a finite sum or not? Well, we pay attention to the common ratio. The absolute value of your common ratio is less than or equal to 1. So this geometric sequence has a finite sum. And the sequence of partial sums of this geometric sequence is convergent. It is converging to what? So that is the question. To the sum of the geometric sequence, which can be nicely computed using this formula. So it's a sub 1. It's a sub 1 over 1 minus r. So it's going to be equal to 10 over 1 plus 1 half. 1 plus 1 half is what? That is 3 halves. Again, 10 divided by 3 halves is the same as 20 over 3 or 6 and 2/3. So this is the finite sum. This is where your sequence of partial sums is converging. Let us open Excel again. The second row are the first 10 terms of your geometric sequence. How do you produce these terms? Well, you encode the formula here. Again, this is the chance for you to know how to encode the formula. And then copy and paste. It will produce you this list. These are ordered pairs. You can plot this. You can look at them as the coordinates of points, and this is the plot. Again, how do you do that? Highlight, click insert, and then choose this icon here. This one stands for the scatter plot. So these are the first 10 terms of a geometric sequence defined by this function. Okay, so what do you notice about this sequence? Look at the sign. The sign or the signs are alternating: positive, negative, positive, negative, positive, negative, so on and so forth. So this is an example of an alternating sequence. What is alternating about an alternating sequence is the sign: positive, negative, positive, negative. And that is the sort of thing that you must expect when you have a factor such as this, when your common ratio is negative. So when you raise it to different values of n, that is bound to produce alternating signs. So just to show to you that they are indeed alternating, this line here is the horizontal axis. That's y is equal to 0. Above that, you have positive terms. And below that, you have negative terms. Let us now produce this sequence of partial sums. That is the sequence of partial sums. How do you obtain the sequence of partial sums? You add the terms one by one. You add the terms to the previous sum. So the first sum is 10. You add negative 5. The next sum is 5. You add the third term to the last sum. 2.5 plus 5 is 7.5. So that is how you produce the sequence of partial sums. With Excel, you just encode the formula and then copy and paste. This is the scatter plot. The orange dots is the scatter plot for our sequence of partial sums. So the first sum is 10. The second sum is 5. The third sum is 7.5. The fourth sum is 6.25. So on and so forth. Now look at that. Using our theorem, our conclusion was the sequence has a finite sum and it must be 6 2/3. That is like 6.66 or 6.67. And that is what we got. Look at here, 6.66. And looking at the scatter plot, that is also what we got. So our collection of points, the sequence of partial sums, they are organizing themselves along this line. And that line there is y is equal to 6.66. Another one. This is a sequence, a geometric sequence. What is the common ratio? It's -1. So the absolute value of that is greater than or equal to 1. So this means this geometric sequence has no sum. It has no finite sum. And if you were to produce the sequence of partial sums, those sequence or that sequence is not convergent. That is another way of saying it is divergent. So this is how you write the general term for your sequence. Okay, so pay attention to this one because this is how you produce the sequence of alternating signs, because this one is again a geometric sequence that shows alternating signs. This is the scatter plot. Look at that. The first term is -4. The second term is 4, -4, 4 again, -4, 4, so on and so forth. This is an alternating sequence. And so I'm showing to you the horizontal axis because above that, your terms are positive. Below that, your terms are negative. What would be the sequence of partial sums for this geometric sequence? Again, how do you produce the sequence of partial sums? Well, you add the terms one by one. So the first sum is -4. Then you add the next term to -4. That is 0. You add -4 to 0. That's -4. So on and so forth. The third row shows the sequence of partial sums. Let us produce a scatter plot for this. That is your -4, 0, -4, 0, so on and so forth. The geometric sequence has no finite sum because the sequence of partial sums, they do not organize themselves around a particular real number. So this one is oscillating between -4, 0, -4, 0. The geometric sequence, which is this, has no finite sum. The sequence of partial sums that arise from this geometric sequence is divergent.